Hello and welcome to lesson 6 of this Introduction to Probability of Wolfram. The topic for this lesson is Bayes' theorem. Let's begin. Bayes' theorem was discovered in 1763 by the English statistician and philosopher Thomas Bayes. While in the last lesson, Assumptions simplified calculations, Bayes' theorem allows you to face head-on the complexity of dependent events. In this lesson, you'll learn about conditional probability, Bayes' theorem, and its consequences in probability theory. Practically, simultaneous events are rare, and most events are sequential, meaning one event may affect the other, and so it would imply dependence. Consider a cat and mouse. The event A is the cat is awake, otherwise it's asleep. Then, event B is the mouse is killed, otherwise it's alive. If the cat is awake, you would expect the mouse to be more likely to be killed, but if the cat is asleep, you expect the mouse to be more likely to survive. This means that writing probability of B for either probability is ambiguous. So to express it more concisely, write probability of B line A, which reads probability of B given A. It's defined as the probability of the intersection of A and B divided by the probability of A. Now, if you just isolate the intersection, you get a multiplication. Applying the multiplication repeatedly, the multiplication rule emerges, this formula. Intuitively, it means that you can indefinitely multiply probabilities as you get more and more precise. For example, in the United States, there's 51.2% of the population that is female. Then 11% of females are smokers, and 11.2% of female smokers will develop lung cancer at some point in their life. So what's the probability that a randomly selected person is a female smoker that will develop lung cancer at some point in her life? Well, by the multiplication rule, multiply all of these as you get more and more precise, and you should get 0.6%. Let's remember axiom 3 for a second. Consider multiple mutually exclusive events that partition the entire sample space. By definition of the conditional probability, you can make any of those B events into a condition. The probability of B index J given A is the probability of their intersection divided by the probability of A. By changing the intersection of a conditional, simply applying the rule again, you get Bayes' theorem. Then, since all of B is a partition of the sample space, the probability of A becomes the sum of the intersections of A and all B's, and so this leads to the extended version of Bayes' theorem. But what's the point? Well, we're now only dealing with B, if you notice. You see, using this, you can infer probability on event A despite minimal knowledge of A, focusing on a single event, B. Let's say at a grocery store, a bin contains 30% of red apples, 45% of green apples, and 25% of golden apples. 20, 30, and 80% of red, green, and golden apples respectively contain more than 27 grams of sugar. If you randomly pick one apple containing more than 27 grams of sugar, what's the probability that it's a golden apple? Using the extended version of Bayes' theorem and all the different B's, calculate the first intersection, then all the other intersections to get the probability of S, and we get 0.506. This theorem has major consequences, but they're a bit theoretical, so bear with me. Let's take a step back. Why is probability theory so practically useful? A major reason is decision theory. The world is full of decisions with uncertain consequences. Will you take a walk if it's likely to rain? Well, it probably depends on the probability of rain. Probability allows you to measure uncertain events with some degree of confidence. With this measurement, you may identify optimal decisions, describe or prescribe decisions based on some consistent rules, or just analyze how decisions are made. But these methods can depend on your approach of probability in itself, namely the frequentist and Bayesian approaches. Let's explain each. The classical and arguably more rigid approach to probability is the frequentist approach. In lesson 4, we gave a frequentist motivation to probability. Probability was the ratio of successful repeated experiments. This approach places frequency as the basis of probability and inherently unbiased. Probability implies prior data. A fair die has a probability of 1 over 6 because it was tested many times, and this is the frequency. President A will be elected at a 59% probability because 59% of virtual tests elected A. This course uses the frequentist approach. Typical frequentist statistics include confidence intervals and hypothesis testing. This is opposed to the more subjective approach to probability, which often phrases itself as probability as a measure of belief. Consider the following probabilities. There is a 0.9% chance that Shakespeare wrote Hamlet. It is 80% probable that President Y will be re-elected next year. It is 75% probable that it will rain in 3 days. None of these events are strictly repeatable. In many contexts, a probability based on frequency is counterintuitive. Future or historical events never happen multiple times. Eliezer Yudkowsky summarizes the Bayesian approach like this. Probability is orderly opinion, and inference from data is nothing other than the revision of such opinion in the light of relevant new information. So here, probability is simply the expression of how much one believes in something. The Bayesian approach equates probability to an event occurrence directly, even if it's the first time it happens. Probability is always conditional. It's based on the prior and posterior knowledge and on current data. This makes Bayesian statistics largely data-driven. A die has a probability of 1 over 6 because you believe a die is fair, and each outcome is equal. President A will be elected at a 59% probability because your belief, based on your prior knowledge of maybe his experience as the Prime Minister of Finance, he will win at a 59% rate. Typical Bayesian statistics include likelihood, Bayesian estimators, and approximate Bayesian computation. Okay, that was a lot of theory, so let's apply a bit. Independent events imply the conditional probabilities are trivial, meaning the probability of A is the same thing as the probability of A given any event. By assuming independent events, the multiplication rule simplifies a lot and just translates intersection to multiplication between each event. The naive Bayes classifier is a machine learning method directly based on this assumption, as it naively assumes independence. In the Wolfram language, it's accessed through the classify function, given the training dataset and corresponding labels, and specifying the classifier is naive Bayes. For example, consider a dataset of 20,000 randomly distorted letters, also called the UCI letter dataset. To use naive Bayes, assume all attributes, meaning the horizontal position, height, pixel total, and so on, are independent. Okay, so load the data of the UCI letter dataset, then make a test example for the letter N, then train the data using the classify. Now, once the training is done, the classifier can categorize data. It identified that these numbers indeed represent N. So what should you remember? Bayes' theorem overcomes the complexity of dependent events by focusing on only one event. Probability can be understood as a measure of frequency or a belief. However, it's also useful to not only give a probability, but also a function describing probability change. The next lessons focus on random variables, also known as functions that describe probability.